Recording now. 5.7 differential equations. What's a differential equation? By definition, a differential equation abbreviating as DE, differential equation, is an equation involving derivatives. So for example, in the previous chapters, I think chapter 2, we learned that dp dt equals kp. That has a solution in the form p of t p0e to the kt. This is called a differential equation. Recall, when we say dy dx, you can write it in another way, y prime or f prime. They all mean the same. And the big question we're going to answer today, how to solve a differential equation. Say we have dy dx equals f of x, a differential equation in this form. What we can do, we can integrate both sides with respect to x, like this. When we integrate both sides, we put the dx there. What do we get here? This will give me the derivative, like the integral of dy is y equals the integral of f of x dx. And it depends on what that function is. Let's say it's antiderivative, it's capital F of x, and we always add a plus c, always. This is called the general solution for this differential equation, because for every c value you get a solution. And the method we're going to be using in this section is called separable. You separate the y's and the x's from each other, so that's why we call it separable. Find the general solution of y prime equals 2x. So how do we do this? Remember, y prime is the same as dy dx. Why did I write it this way? Now it's easier to separate. You can move the dx to the other side, like so. Then we can integrate both sides. This is y equals to the antiderivative of x is x squared over 2 plus c. The 2's cancel each other, so then y equals x squared plus c. Same thing for, let's say, 3x squared minus 4x. We need to find or solve this differential equation or find the general solution. So how do we solve such equation? Again, we rewrite dy dx, keep the right hand side the same. Now we separate, we bring the dx to the other side and integrate both sides. Y equals. To find the antiderivative for this or the integral, we integrate them one at a time. The integral of x squared is x cubed over 3. The integral of x is x squared over 2. Don't forget the plus c. Simplifying gives me x cubed minus 2x squared plus c. So that's the general solution. Now we got this. How do we verify that this is really the solution for the given differential equation? So to verify this, we find its derivative. We find y prime. So what is y prime? It's the derivative of x cubed, which is 3x squared, minus derivative of 2x squared, 4x, plus the derivative of c is 0. So we got y prime is 3x squared minus 4x. If you look at this one and the given equation, they match. They should match. Should be the same. Another one about verification. Let y prime equals 2xy. Verify that y equals ce to the x squared is a solution to this given differential equation. They're not asking you to solve it, but they're asking you just to verify it. So how do we verify this? Well, we're going to find the derivative, right? But before we find the derivative for such a function, on the side, recall if y equals e to any function, then y prime, it's u prime times itself. So I'm going to take the left hand side of the equation, which is y prime, try to find what that is, y prime. Keep the constant. What's the derivative of this? Well, it's the derivative of the exponent times itself. So derivative of the exponent is 2x, so 2x ex squared. That's the left hand side of the equation. I'm going to look at the right hand side and see if they match or not. The right hand side is 2xy. They don't look like they match, but if you look in the left hand side here, there's only x's and c's, no y's. So what I'm going to do here, I'm going to replace this y with the given thing, ce to the x squared. And if you simplify it, what do you get? 2cx ex squared. They match. So that tells us that y equals ce to the x squared is a solution. This is the general solution because of the c. Now, if c takes a value, like c, you were able to find that c is 2 or something, then the solution is called a particular solution. Solution is called particular solution. So to apply that, we can ask you find the particular solution of the differential equation 3y squared dy dx plus 2x equals 0 when y of 0 is 3. So to do that, we need to do separable first. So we keep this here. We subtract 2x on both sides. Then I want to get the dx to the right hand side, like so. Look, on the left hand side there's only y's, on the right hand side only x's. Now we integrate both sides. Keep the 3 out. The antiderivative of y squared is y cubed over 3. Keep the negative 2 out. The antiderivative of x is x squared over 2. And don't forget the plus c. The 3's cancel, so you got y cubed equals the 2's cancel, negative x squared plus c. Notice they give us a condition. They said y of 0 is 3. So y of 0 is 3. This means when x is 0, y is 3. So 3 to the third equals negative 0 squared plus c. So 27 is c. Then you're going to put that back in here. So you get y cubed is negative x squared plus 27. So for this particular value for c, this is called particular solution. It doesn't have to be always x and y. It could be like different variables. They can ask you to solve something like dr dt equals negative 0.35 r. So how do we solve something like this? We need to separate the r and the t using separable. So we're going to separate them. So how do we separate them? We bring the r down here and move the dt to the right side. Then integrate both sides. the integral of dr over r is natural log of absolute value of r equals, take the constant out, dt. Here you can drop the absolute value, no need for it for now. The antiderivative of dt is t, and don't forget the plus c. You can just leave it like this. If you like to solve for r, the way it works, we do e both sides like this. E both sides. And we have a property in logs, e natural log of anything is the thing itself. And this one you can break it into two terms, e of this times e of c. E of c is just a constant. You can put k, w, c, capital C, anything you like. So that gives you exactly what r is. Let's apply it a little bit now to something. Let's say Marlene invests $1,000 in an account that earns interest at a rate of 4.5%. compounded continuously. Find the particular solution of the differential equation that describes the growth in value of this account. So to do this, we start by letting A of t be the amount in dollars, of course, in Marlene's account after t years. We have from before, from previous sections, we had this differential equation dA dt equals Ka, which came from compounding continuously equations. And to solve this, we do separable. We bring the a down and the dt up to the right. So I'm going to do all this work before we start applying the given information in the problem. So we integrate both sides. Natural log of a, kt plus c. Then we do e both sides. E both sides. That gives us a equals, you can separate these by the properties of exponents. CE to the KT. If you read the problem, they said, find a particular solution. This is a general solution. How do you find the particular solution? Well, let's see what they give us. If we read through this, they give us the rate, that's K. So K is given 0.045. The initial amount that she started with, so at A of 0 is $1,000. So let's put that in. A of 0 is 1,000. So A of 0 is 1,000. So that means I can substitute when T is 0. Okay, when T is 0, this was 1,000. So 1,000 equals C times e to the 0. Anything to the 0 power is 1. So that gives me the C value. We're going to put that back in. So we get A equals C is 1,000, E, K is 0.045, and T. That's the particular solution. Note, A prime of T over A of T. This, the fraction or the number, this number represents K. This number represents K, which is the continuous growth rate, just in case if you're asked about it.